Okay, talking about resets, we talked about this a little bit before when we are doing Verilog, synchronous resets. Clocked reset, watch out for synchronous reset. We're going to call it RSYN, built into flip-flops. RSYN, or synchronous resets, must not be fed into an asynchronous circuit. This is like number one problem that often people get into. Number one digital design problem, not doing the reset correctly. So if you press this reset, there's kind of two problems. One is when you press the reset, you get this clear signal. It's an asynchronous signal. So it takes one clock cycle before you actually reset. That's usually not a big problem. But you may have a situation where you want the reset to happen right away, but generally speaking, that's not. But the real problem with this circuit is that when you release the reset, you could release the reset once in a while. It'll be right on this clock edge, and some of these flip-flops will come out of reset and some will not. And so then again, you can have multiple child states that differ by more than one bit. So the reset signal should be synchronized on release. That's the problem. It is normally not necessary to synchronize the start of reset. This is only temporary, one clock cycle. False state one can enter when reset is pushed. So you have the same problem. When you push the reset, some may reset, some may not, but that's only one clock cycle. Generally not a problem, but depends on the situation. But the real problem here is the reset has to be synchronized on release. Otherwise, you go to some crazy state that you didn't want.
How do we get to a case where our reset signal won't be synchronized on release? Like, what would that case be? Because like here, it looks like when we clear that line, that we should be clearing that line all at once,
Well,
But
so
is there a case where that's not the case?
well, no, it's true that it's all the cases that's not true. When you release this signal, this is a wire, right?
Mm-hmm.
And this wire, there's delays along the wire, no matter what you do, right?
For sure.
This could be 1 attosecond. I don't care. Difference between them, it doesn't matter. If it so happens that this clock edge, this flip-flop saw it, and this flip-flop didn't see it when you release this, and you can never make it at the exact same time, then one will come out of reset and one doesn't.
So how do you go about synchronizing it?
How do you go about synchronizing it? Well, we're just going to show that. So if I pass it through a flip-flop now, this clear signal is now a synchronous signal. And now we have a synchronous clear, which is okay. Reset the ladder stops. No, it's a synchronous signal, but we still have a problem in here in that here's a synchronous signal going into a clock divider. We talked about this before. If I have a clock divider that has a synchronous reset, I may reset this before the clock comes, and then these things never clock in the reset. That was an example. Remember, I gave you this example. Oh, I had this problem at work where I had a little oscillator, and then sometimes it wouldn't oscillate, the clock wouldn't come in, and then I never get the load in the right value. This can still happen here. Here's a situation where I have a clear signal. It's synchronized now, so it's a nice synchronous signal, but it's going into a circuit that generates the clock for a bunch of other flip-flops. And if this gets reset first, there's no clock. These never get clocked in and they never get reset. So you got to be careful with synchronous resets if you have dividers that are used to clock other circuits. So the preferred, highlighted in red here, is to asynchronously apply the reset and synchronously remove the reset. So that's what this circuit at the bottom does. We have a reset signal here, asynchronous button push. So this is asynchronous right here. And you'll see that this asynchronous signal, it bypasses this synchronizing flip-flop and it goes right into this OR gate. And so if this goes high, this will create a reset here. And we'll use asynchronous reset here for these flip-flops, which guarantees that they'll reset right away. So the minute reset goes high, clear goes high. We don't even need a clock edge here, right? And we reset the flip-flops. And then As long as you hold reset for one clock cycle, then this was a 1, and that 1 passed through here. And normally the reset would run for hundreds of clocks. You hold it for quite a long time, but as long as it's one clock cycle, there's a 1 here. And so when this goes to a 0, when you release it, it goes back to 0. This 1 holds it there. So this doesn't go to 0 right away. It doesn't go to 0 until this nice synchronous signal goes to 0. And only then, with this synchronous signal, which makes this synchronous here on release, does this come out of reset. So we've asynchronously reset it, and we synchronously remove the reset. And so you see this clear signal comes out just a little bit after the clock edge, it goes low. So it's synchronously coming out of reset for all these flip-flops. So that's the preferred method. When you have a circuit that you have to guarantee that it gets reset correctly, that's what you want to do. Does that make sense? And I said the resets are very tricky. Got to do them right. Okay, the next thing we're going to talk about is logically related or logically encoded signals. And it turns out logically encoded signals happen all the time. For instance, when we talked about